So in the previous class, we were discussing with the spectrochemical series, and we have also seen that how to apply that spectrochemical series. So we have the ligands and all these nitrogen containing ligands, especially ammonia, you should remember. NO2, CN and CO, these four are very common ligands. Okay, they are all nitrogen containing ligand, they are strong field ligands. SCN and NCS. What's the difference between both of them? Any idea about that? SCN and NCS. So it is an ambidentate ligand. Ambidentate means it can be connected from both the sides. And if it is SCN written, means it is connected through sulfur. But if it is NCS written, it is connected to nitrogen. So as I told you, the nitrogen, most of the nitrogen containing ligands are strong ligands. Right? So this is, we have applied the spectrochemical series on various complexes. Strong ligands will pair up the electrons, while weak ligands let them remain as it is unpaired. Right? I have told you, Aisha, in the last class that if you have four ligands and they are strong ligands, so then you are going to, and if the pairing is possible, then you are going to form a square planar complex. Clear? Strong ligands. But if they are weak ligands, you are going to use sp3 hybridization. Okay, and they are going to remain as it is. Got it? So just we will try to figure out what is going to be the hybridization of scandium. We will do some more revision questions to connect us from the previous class, and then we will proceed ahead to the next theory of bonding. Okay. So next is scandium with 6 aqua ligands, and you have +3 charge. I can help you out. The first thing we need to know is scandium, the atomic number is 21. The precise, that short hand representation of the electronic configuration is argon. It is the 21st element. So 4s2, then 3d1. Right? And in our question, in our complex which is given to us, it is scandium +3. We need to remove 3 electrons, and as you can see, all the 3 electrons from 4s and 3d will be removed. So I'm going to write the scandium again with the +3 charge, and that will be argon. This 3D 4s and 4p are completely empty because there was only single electron in 3D that also was removed while making scandium 3 plus ion. Now we have 6 ligands. So what should be the geometry for 6 ligands? Aisha and Marwa, tell me. What should be the geometry of 6 ligands? Either it should be
octahedral or
yes. And what is the hybridization? Octahedral, exactly. And what should be the hybridization?
D2sp3.
Either if it can be D2sp3 or it can be sp3d2. It depends which type of d orbitals you are using. If you are using the 3D orbital which are inside before 4s, it means the hybridization is going to be D2sp3. But if you are using the outer d orbitals 4d, okay, then sp3d2. Inner d orbitals you are going to use only if they are empty, if they are available. You cannot use them if they are completely filled. And in this example, you can see that 2d orbitals are empty, right? So what we are going to do over here is we are going to take 2 of the d orbitals, right? And one s d2sp3 is going to be the hybridization, and the water aqua ligand is going to donate its lone pair. So these are the pair of electrons donated by water of the aqua ligand. And it is going to be D2sp3, not sp3d2. It will be octahedral. In the case of ordination number 6, geometry is not changed by hybridization. So this is going to be the complex. It is going to be diamagnetic. As there are no unpaired electrons, its magnetic moment is going to be 0. Number of no unpaired electrons were there, because whatever the electrons were there, they have already been removed. Okay. So diamagnetic, magnetic moment 0, octahedral, D2sp3. These things are going to be asked, okay? That explain the geometry, explain the hybridization of the complex. I hope this is clear.
Yes, sir.
NH3 is a strong field ligand. Aisha, am I audible?
Yes.
Strong field ligand. Zinc is the 30th element, okay? And zinc, its electronic configuration is argon. 30th element means all 4s2 and 3d10, all the d orbitals are completely filled. Okay, this is the zinc. In the complex, we have zinc 2 plus. So we need to remove 2 electrons to make zinc 2 plus, because the complex, the zinc is having +2 charge. So we are going to write it argon 3d10 4s 0. How it will look like if I represent it in the form of the boxes. Four s is emptied because we need to remove 2 electrons. 4p is there, but it is already empty. But the D subshell is full. Argon 2 plus, zinc 2 plus is there, and this is the electronic configuration of the zinc 2 plus, which you can see on your screen. And there are 4 NH3 groups, ligands. NH3 is a strong field ligand. Strong field ligand will force the unpaired electrons to pair up. So tell me what is going to happen. What is going to be the hybridization of this complex? Shape of the complex and hybridization of the complex. One thing we need to know
SP.
is, yeah, sp3 or dsp2. Yeah, Marwa, we have 2 options. Either we have sp3 or dsp2.
SP3.
sp3. Why not dsp2?
Because d orbital is completely filled.
Yes, d orbitals are completely filled, so there is no room for pairing. Normally, what normally mistakes are made by the students. They think that the NH3 is a strong ligand and it will pair up. Okay, but there is no room for pairing because all the d orbitals are completely filled. So it is going to be sp3, very correct. And what is going to be the shape of sp3, Aisha?
Tetrahedral.
Tetrahedral. Exactly, it is. So it is not that always with the strong field ligand you are going to have square planar complex. No. With the strong field ligand, if there is a possibility of pairing, then only we can pair the electrons and the inner d orbitals will be made available for bonding. Then we will have. So it is going to be a tetrahedral. It will be like this. It is tetrahedral geometry is like the outer boundaries are like the pyramid, and at the center of the pyramid you have the central metal atom or ion, while the 4 ligands are pointing towards the corner of a pyramid or a tetrahedron. Got it? So this is going to be similarly for NiCO4 also. It is going to be tetrahedral, right? So let's move to the next theory. And that next theory is the crystal field theory. We call it CFT. Okay. In CFT, actually, there are a lot of assumptions, okay, which are not true. But those assumptions, if we leave those assumptions, there are certain points in the crystal field theory which can help us to understand the bonding more clearly. One thing which is missing in the VBT, valence bond theory, is that why the strong field ligands force the unpaired electrons to pair up. That we have not seen. We have not seen the energies of the d orbitals, how they change in the presence of ligands, what happened to the energies of the d orbital. So we need to look into those details to get the actual idea of the bonding. And CFT actually helps us to understand those energy, more detailed aspects of the energies of the d orbital. Okay. So first of all, assumptions of CFT. So can any one of you help me out? What assumptions crystal field theory is having? Any idea? So what CFT is about? CFT explains the splitting what this splitting means. Splitting of d orbital. Aisha, Marwa, tell me what this splitting means. Splitting actually means that the d orbitals which were having equal energy, their energy became unequal when the metal is present in a complex surrounded by ligands. Is it clear?
Yes.
So that's what splitting means. Splitting means doesn't mean that the d orbitals are going to split. They are going to remain in an atom. But with respect to energy, they will not have equal energy. So crystal field theory actually explains us what how the energy of the d orbitals get affected when the metal ion is surrounded by ligands. Okay. So that's why the name is splitting of d orbitals. Okay. There are certain assumptions in CFT. So, and they are not true, actually, they are assumptions because CFT doesn't explain anything about the assumptions. Assumptions, regarding the assumptions, you can get the explanation from VBT. Okay. So actually they complete each other. So there are some points which VBT explains us, and there are some other points which CFT is able to explain us, right? And by combining both of them, you have the complete idea of the bonding in complexes. Okay. So in the CFT, the biggest assumption which is not true, we know that, is the interaction between the metal ion and its ligand. So this interaction is assumed to be purely ionic in nature. What actually it means? It means that the metal ion, but this is not true, we know that. The metal ion and its ligands, they are not connected by covalent bond. Okay. They are actually connected by electrostatic force of attraction. If they are ions, if the metal is positively charged and the ligands are negatively charged, so they are going to hold each other by electrostatic force of attraction. Or ion dipole interaction. So this interaction is assumed to be, it is not assumed to be covalent one, but we know that this is not true, because we know that VBT ligands and the metal ions, they form coordinate covalent bond. But this is just an assumption here. So don't get affected too much by this point. We know that it is a coordinate covalent bond. Okay, this is not the real thing which crystal field theory is trying to explain. Okay. Crystal field theory is trying to explain some other thing which we should focus on that thing. So whenever the metal ion is in the isolated state, the d orbitals of the metal ion of the 3D subshell are of equal energy. Okay, this is the d orbitals of the metal ion. Look here, and what am I writing? I'm writing in the bracket gaseous. What it means? It means isolated gaseous ion. So d orbitals are of equal energy. Got it? And there is a name which tells us that they are of equal energy. That name is degenerate. Is it clear? Aisha and Marwa? So what do you
Yes,
mean
sir.
by degenerate orbitals? Mean they are of equal energy. Got it?
Yes.
And when the d orbitals have the equal energy, all the 5 d orbitals have the equal energy. When the metal ion is alone, it is not surrounded by any ligands. Then you have the equal energy. But if the metal ion is present in a complex, if it is present in a complex, there you will observe the splitting in energy. Splitting of d orbitals of the metal ion in octahedral complex. So when the metal ion is surrounded by ligands, as you can see in this case, this is the metal ion which is surrounded by 6 ligands, and you can see this is an octahedral complex. So what will happen to the energies of the d orbital? My first question is very simple. Are they going to remain same?
No.
They are going to change. They are going to remain same only if it is an isolated atom of ion. How they are going to change? They are going to change, that is known as splitting of d orbitals. And the pattern of splitting depends upon the number of ligands, nature of ligands, and the geometry. So how these d orbitals are going to split? In an octahedral complex. So they are going to split into 2 groups. One group consists of 2 of the d orbitals. They are having higher energy, higher than the average. Okay. And this group of d orbitals is named as EG, set of orbitals. This 2. So 2 orbitals and 2 letters EG. Okay. And T2G. For the another group which actually has energy not as high as that of those of EG orbitals. Okay. What this EG and what this T2G means, that is not of any significance to us, because this is related to spectroscopy. octahedral splitting EG consists of axial set of d orbitals. So there are 5d orbitals, as you know, if you and so out of those 5 orbitals, I will explain the diagram also to recall what you have studied in your 11th, and so that we can relate whatever I am writing here now. And there are 5d orbitals. 2 of them are along the axis, x-axis and the y-axis and the z-axis. And they are dx2 dash y2 or dx square minus y square, and dz square is along the z-axis. And there are 3 of d orbitals which are not along the axis, they are in between the axes. For example, dxy is in between x-axis and y-axis. dyz, dzx. Got it? So these are the 5 d orbitals. Is it clear?
Yes, sir.
So dxy, dyz, dzx. Okay. So how they look like in an atom? If this is the atom, okay, and atom you can take the axes, okay, and you can at the center of them, all of them, you can take nucleus. So you have x-axis, y-axis, and z-axis. Arbitrarily, you can assume 3 perpendicular lines passing through origin, and this is the nucleus, of the metal ion. So dz2 is going to be like this. Got it?
Yes.
It is along the z-axis. That's why it is called. This is the electron cloud actually. It looks like part of it is look like p orbital, and there is a circular electron density present around it. Okay, this is the electron cloud. Okay. Similarly, you have dx2 dash y2. So I'm not showing all the 3 axes to make the diagram simpler. Okay, this is the x-axis and this is the y-axis. Z-axis is perpendicular, it is coming out of the plane of the paper. I'm not showing it just because I don't need it. And dx2 dash y2, there are 4 lobes of that orbital, and those 4 lobes are along the x-axis and y-axis. So these two constitute the EG set of orbitals, the orbitals which are pointing, which electron densities are present on the axis. Okay, and there are 3 orbitals where the electron density is not present along the axis but in the middle. For simplicity, I am not showing all the 3 axes. I am showing in each diagram, I am showing only those axes between which the d orbital is present. Okay, dxy. Okay. It will have 4 lobes. And the electron density will not be along the x-axis and y-axis, but in the middle. Y and z axis. Okay. Arbitrarily, I am drawing the axes. Okay, I'm not showing the actual 3-dimensional atom, but I'm showing only those axes of the plane in which the d non-axial sets of d orbitals are present. So these three d orbitals constitute the T2G set of d orbitals, which are non-axial set of d orbitals, and those two d orbitals constitute EG. Got it? So how this is going to impact the energies of the d orbital, splitting of the energies of the d orbitals in a complex. So let's see. So suppose if the pattern is going to be different in different arrangements. This pattern is only for octahedral. Got it? Not for the
Yes, yes.
tetrahedral complex. Tetrahedral, it will be different. Okay, so what you can assume is this is the metal ion, right? And the metal ion is at the origin, and there are axes, x-axis, y-axis, and z-axis. Okay, and assume, because it is an octahedral complex, you can assume the ligands are getting connected to the metal ion. They are approaching the metal ion along the x-axis, y-axis, and z-axis. Okay, that's how we can think of the octahedral arrangement. Octahedral arrangement. Okay, so there are four groups present in a plane. They are approaching at 90 degrees with respect to each other, and one group is approaching from the top, another group is approaching from the bottom. So this is octahedral arrangement that you know very well. It consists of 6 ligands, and normally we show ligands in an arbitrary manner, but for the sake of understanding, we can think that these ligands are approaching along the x-axis, y-axis. I hope all of you are getting my point, and the z-axis. Got it? Is that
Yes.
is that clear, Aisha, Marwa?
Yes.
Yes, sir.
So now the orbitals which are directly along the axis will face higher repulsions from the lone pair of the ligands. More repulsion will be faced by the electrons present in the d orbitals which are along the axis. Look here. And if they face more repulsions, their energy is going to be higher because repulsion will cause increase in energies. Got it? But not all the d orbitals are facing the ligands. Suppose if this pencil is a ligand, okay, and if it is connected to the metal ion, okay, along the x-axis, so you have dx square dash y square. Its low are along the x-axis and y-axis. Okay, if one ligand is approaching the metal ion from the z-axis, okay, so you have the orbitals, d orbital on the z-axis, and that is dz2. So that dz2 will face more repulsion from this ligand, and its energy will be higher. So you can see this is why these two d orbitals have higher energies, while the other three d orbitals, dxy, dyz, dzx, which are non-axial and Their lobes are not along the axis, they are in the middle at the angle bisectors. They are not, they will be repelled, but not up to the extent up to which dx square dash y square and dz square are repelling. Got it? So their energy will be raised, but not as high. That's why you can see that T2G are placed below EG. This gap will be there, and this gap in the energy of the d orbitals of the same metal ion. The d orbitals they are still there in the metal ion, but now they are not of equal energy. There is a gap, and this gap is denoted by the symbol delta O. Okay, delta is the difference. Got it? Delta O. O represents the octahedral complex, octahedral group. Delta is the difference in energies of the d orbitals in an octahedral complex. Is it clear?
Yes, sir.
So the d orbitals which were having equal energy, they were having equal energy only when the metal was not connected to any ligand. But if the metal is connected to 6 ligands, the two of the d orbitals will face more repulsions, and their energy is going to be raised more than the other 3 d orbitals which are non-axial. This gap between the energy is known as delta O. Okay, and this is known as crystal field splitting energy. Got it? Average, if you compare from the average energy you can take as the energy of these 5 of the d orbitals. So these 2 d orbitals have, there are 2. This average is known as barycenter. And these 2 d orbitals have 3 by 5 of delta O, the 3 by 5 is the part which is higher than the average. And the energy of T2G is, there are 3 orbitals, okay, in T2G. So minus 2 by 5 delta. Okay, this average energy is known as barycenter. Okay, so this whole gap is delta, and as you know that the axial orbitals, set of d orbitals, will face more repulsions from the incoming ligand, so their energy will be raised higher than the average energy. How much higher? 3 by 5 times of the whole gap delta. Okay, and a non-axial set of d orbitals, their energy will be raised less than the average energy. How much less? Minus 2 by 5 times of delta. Okay, so it is just like a center of mass. Okay, M1, X2, M2, X1, right? Like that. So there are 2 d orbitals, energy 3 by 5, and 3 of the d orbitals having lower energy, minus 2 by 5. Got it? Is that clear? This is the average energy of the d orbitals excited state. Is that clear?
Yes, sir.
So now how this splitting is going to be impacted by the ligands? First, it is going to get impacted by the geometry. So all the octahedral complexes will have this kind of split, in which the D Z2 and DX2 dash Y2 have higher energies, while DXY, DYZ, DZX have lower energies. In all the octahedral complex, the pattern is going to be same, right? But the gap is going to be different. Are you getting my point? The pattern will be same, but the gap is going to be different. How is it going to be different? If you have weaker ligands, okay, if you have weak ligands, the gap is going to be less. They will cause less repulsion to the d orbital. The gap delta O is the gap. Smaller gap will be there. Got it?
Yes, sir.
And strong ligands will cause higher repulsions. So gap will be more, right? Delta O, crystal field splitting energy, will be more. This gap is going to govern, okay, how this filling of d orbitals take place. Whether we have to pair the unpaired electrons or leave them unpaired, okay, everything is decided by the gap. Whether it is smaller gap or larger gap, and who is going to decide the gap? The ligands. So CFSE actually classify the ligands by their strength, and this point we have already included in valence bond theory to make it more useful. But actually this point is actually from the crystal field theory. Spectrochemical series in which the ligands are arranged in increasing order of their strength. Got it? So this is basically from CFT, not from VVT, but we have included in the, and we have seen I, BR, SCN, right? We have seen, right, CL, S, right, F, OH, oxalato, aqua, and you have nitrogen ligands in CS. ETTA, NS3, pyridine, ethane 1,2-diamine or ethylene diamine, nitrite or N, cyanide carbonyl, strong and weak. Strong more gap, weak less gap. That's it. More delta. Okay. Is it clear? And how this gap is going to affect the filling of electrons? This is also very easy. But in VBT, we have not done this much of details. As you can see, in VBT, we have just said, okay, strong field ligand will pair up the electrons, weak ligands will let them remain as it is. Got it? I hope this is clear to you.
Yes, sir.
So now let's take two examples side by side. Both are octahedral. Iron plus 2. The metal ion is also same. For the sake of comparison, they are both octahedral. They are both in plus 2. Iron is in plus 2. In both of them. Got it? So just for the sake of comparison, we will try to look how the d orbitals, energy of the d orbitals is going to get affected by the nature of the ligands. This is also Fe2 plus. How many d electrons are there? Tell me. You need to remember the electronic configuration, very, very important for you. Iron is 26th element. So how many electrons it was having? 26th element. Yeah. Tell me. How many electrons? 6. I mean 2 and 6. Okay. 26th element. But as you can see here, that iron is having the plus 2 charge. Okay. So plus 2, that 2 electrons are remaining. Got it? So you have just argon 3d6. But actually, this is not the real picture. Okay. The real picture, in order to get the real picture of the energies of this and the filling of the d orbital, you need to use CFT. VBT tells you that okay, we will pair the electrons because Cn minus is strong ligand. But why actually it is getting paired, that is not known. But now you can clearly make out why the pairing has occurred. Aisha and Marwa, can you see this? Dear vitals.
Yes, sir.
So what's the difference? They are the same d orbitals in both the iron. The difference is of
Strong ligands and weak.
strong ligands and the weak ligand, and that will result into the splitting pattern, the splitting gap. You can see Cn is weak, a strong ligand. So the gap is higher, larger in this right complex, and the gap is smaller, right? So I need to put Aisha 6 electrons. Okay. Now I'm putting the 6 electrons. I'm going to follow the method which is going to give me an arrangement which is having lower energy, right? More stable, right? So let me start filling the 6 electron. First, second, third. How many electron do I need to put? 6. Got it? Till these 3 electrons, I don't have to think at all, because the d orbitals are of equal energy. So why to pair them unnecessarily? Just put them one each. Okay. Hund's rule of maximum multiplicity. You might have studied in class 11th. That is followed. Now we need to think from the 4th electron. Okay. So Aisha and Marwa, where should I put the 4th electron? Tell me, where should I put the 4th electron? Should I put it here itself? Or should I put it in easy or
For
right?
the weak one, we need to add another for us.
No, till now we don't require 4s. These are d orbitals, 3d orbitals, 6 electrons are there. Okay, I put the 3 electron, 3 yet to be put into this d orbital. So I put the 4th electron, 2 more I will put. But I'm asking one by one. Okay, where should I put the 4th electron? And should I put it along with these 3 electrons? Or should I put it in the higher energy? Answer is whichever is more stable. Okay. In this case, or you can think of PBT. VBT said that this weak ligand electrons will remain unpaired. Okay, so don't pair them up. Got it? Just try to keep them unpaired as much as possible. Clear or not?
Yes, sir.
If you get into the detail, this pair, the higher the ligands are weak, so the gap is very small. So why to pair them up? Because pairing requires energy, repulsion will be there. The pairing will have more energy, and the delta of that splitting is very small. So just let them remain unpaired. So 4th, 5th, and now 6th electron, definitely I'm going to put it here, right? Is it clear?
Yes.
Now look in this complex, the right one. Cn minus is strong, again the gap is higher. So 3 electrons I have already put. The 4th electron, why I will not going to put it at the higher energy, because the gap is too large. So electron will be at the lower level. Are you getting my point? So here the gap is more than the pairing energy. So gap was higher. So electron were not able to go to the higher energy level. So they prefer to stay at the lower level. That's why the pairing occurred. In the left case with the aqua ligands are weak field ligands. They are not able to cause more repulsion. They are not able to cause the large gap between the d orbitals. If the gap is small, it doesn't matter. So because not much gap is there. So let the electron remain unpaired. But if the gap is more, don't put the electron at the higher energy level. Okay, just put them in a more stable way, and that is follow the pairing and put them at the lower energy. Got it? Is it clear or not? Any doubts, Aisha, Marwa, tell me. Just look at it carefully. Small gap, weak ligands. Okay, smaller gap. If the gap is smaller, you will prefer to keep the electrons single. But if the energy gap is very large, you are not going to take the electron to higher energy level, you will put them at the lower level. Because that putting them at higher energy level because of the larger energy gap will make them unstable. So Aisha and Marwa, is that clear or not? Tell me. Very, very important thing. You need
Yes,
to
sir.
understand. Or you can just, if you are getting confused in it, very simple way to remember it, what we discussed in VBT. In VBT, it was said that the strong ligands will force the unpaired electrons to pair up. So electrons are paired. While in the weak ligand, the electron remain unpaired. But actual thing was not told. Now we have the actual thing. It is the gap which is making the electrons paired or unpaired. Strong ligand, the gap was large. Large gap. So the electrons were not able to go to the higher energy level. They prefer to stay at lower energy level, and that's what caused the pairing, right? And in the weak field ligand, the gap was very small. So why to make them crowded? Why to pair them up? Okay, let them remain unpaired. The gap is energy is very small. Difference in energy is there. So let them stay unpaired only. Okay, that's how the CFT is working. Is it clear? This is helping us to make us understand the actual reason behind the pairing of electrons. Got it? This electronic configuration, I can write it as T2G 4 and EG 2. There are 2 electrons in EG and 4 electrons in T2G. This electronic configuration is T2G. Okay, the 3 orbital T2G. 6 EG 0. Got it? Is it clear or not?
Yes, sir.
So, what is the crystal field stabilization energy? There are 6 electrons in T2G. There are 4 electrons in T2G. The energy of the T2G was lower. So I'm going to put the minus sign, lower than the average. Look here what we discussed. Lower than the average. How much lower? Minus 2 by 5 delta. But there are 4 electrons at this lower energy level, each having energy minus 2 by 5 delta. and there are two electrons at the higher energy level. The higher energy level, each is having energy of 3/5 delta. Got it? So the overall, and there is one repulsion caused by pairing energy. Okay. So -8 plus 6 minus actually this is to pairing energy is actually caused by the repulsion of the electrons. So this minus sign indicate the lowering of energy. Okay. Let's see what is happening in that other complex. There are 6 electrons in T2G. T2G were 3 orbitals. Each one is having lower energy of 2/5. 3 orbitals are 2/5 times delta. And there is no electron at the higher energy level. Got it? So the overall stabilization is going to be higher. Is it clear or not?
Yes,
So which complex is more stable? Very, very important. Okay. So what is the energy of the d orbitals? Okay, if there are two, make them higher plus 3/5. 2 means 3/5. Out of 3/5 means out of 5, 3/5. Okay, and 2 orbitals. And the lower energy levels are -2/5. So based on the number of electrons present in those orbital T2G, we calculated the algebraic sum of the energies and we realized that this is 3p because there are 3 pairs. Normally this pairing energy is neglected because it is very small. So you can see that this right complex is more stable because you will see that its energy is more negative, means it is stabilized by a larger extent. Is it clear?
Yes, sir.
So this is how it works. Okay, if they give you the numerical, normally they don't get into the numerical much, but you need to understand the basic idea what is happening. Okay, what is being why the electrons get paired. The electron get paired because there is higher splitting of d orbital happen, and that's why the electron don't prefer to go to the higher energy. They continue to occupy the lower energy level, and by doing so they will get paired up. And if the energy gap is small, so why to pair the electrons unnecessary? Let them remain unpaired. Okay, so electron are filled as they used to get filled in the atom. Okay. They will not get affected by the energy level. Okay, the pairing will not occur until unless each electron is single, each or d orbital is singly occupied. Is it clear or not? Any doubts on this? Okay. Now we need to understand one more thing which is very, very important. This gap is of octahedral complex. Okay. This is the gap in the octahedral complex. So this is the metal ion in the isolated gaseous atom. And if that metal ion is surrounded by 4 ligands, the pattern of splitting is going to get reversed in a tetrahedral complex. In a tetrahedral complex, dxy, dyz will have higher energy, and dx2 dash y2 and dz2 will have lower energy. So it is entirely reversed. This gap between the energy of the d orbitals is known as delta t. Okay. If you try to compare the increase in energy, of the dxy dyz, there are 3 orbitals, so the increase is 2 by 5. If there are 3, it is 2 by 5. Delta t. Delta is a gap, t is the tetrahedral, and this is minus 3 by 5. This you need to remember. Okay. Is it clear?
Yes, sir.
So it is reverse actually. So this is how the filling happens. Tetrahedral complexes are formed with a weak field ligands. So generally they are high spin only. Okay, because they are a weak ligand, the gap is small, and because the gap is smaller, the electrons are going to stay single. They are going to get paired up only in the strong field ligand, in the presence of ligands octahedral complex where the ligands are very strong and they were causing more repulsions. Got it? Is it clear or not?
Yes, sir.
Now, so VBT and CFT, now we can see the similarities. VBT actually first, original VBT was not able to differentiate between the strong and weak ligands. But now we know that VBT is actually has adopted that strength of the ligand from CFT, and with that it works more appropriately, right? So strong ligands will pair the electrons, weak ligand will let them remain unpaired. Actually, strong ligands will cause more gap in the d orbitals. That's why the electrons are filled at the lower energy level, they become paired, right? That's what the reason is. Very simple. Now we need to look at the color of the complexes. This is the application of CFT. So can both of you tell me what is the color of copper sulfate solution? Aisha and Mara, tell me.
Greenish.
Blue.
Pardon? It is light blue colored, right?
Yes.
Greenish marwite can form greenish if it is with chloride, right? Copper sulfate in water is light blue. So most important application of CFT, crystal field theory, is the color of the complexes. So first thing I need to explain it to you that the color is because of the so the color occurs due to DD transition. What is this DD transition? Any idea about it? DD transition. Okay, actually the electrons absorb the energy and move from lower energy d orbital to higher energy d orbital temporarily. And when that happens, they absorb certain colors. So whatever the colors are absorbed, they are not visible to us. The color which are complementary to them are visible. Okay. So first and the foremost thing is the colors are due to, in most of the cases, the colors are due to DD transition. It is the electronic transition, temporary electron transition, in which the electrons are moving, continuously moving between the d orbitals by absorbing certain wavelengths. Okay. And the color which is visible to us will be complementary to the color which is absorbed. So you just make the color wheel. The color wheel is made up of actually the all the colors which are present in the sunlight. Okay, sunlight actually has that all the colors. So copper sulfate solution is actually, it is appearing blue to us. Why it appears blue? Because it absorbs orange color from the visible light. Visible light has 7 colors. Okay. And if orange color is absorbed, that the light which is coming out of the copper sulfate do not contain that orange color, so it will be opposite. The color which is opposite to that orange color in the color wheel is blue color, and it will appear blue to our eyes. Got it? So this is actually the application of CFT. So I will draw the color wheel. So it is appearing blue because the orange color is the absorbed color. So that whole white light is made up of these colors, you know. And orange color is absorbed by the copper sulfate. So this is missing. And if this is missing, what color will be visible to our eyes? The color which is visible to our eyes is the opposite color. Okay. This is the visible color. So why copper sulfate appears blue? Because it absorbs blue color. Okay. So this is why it absorbed, because it happens due to DD transition. Okay, so let's get into the details in the next class. Okay, and very good questions, very easy and very good topic.